have any questions or need anything before we get started? All right. Well, last time we began chapter 8, which involves looking at some more angular concepts and how they relate back to their linear counterparts. Once again, if anything can be used to describe linear motion, it likely has an angular counterpart to describe rotation instead of moving in a straight line. We began this discussion by looking at torque, torque being the angular counterpart to force. Whereas linear force causes linear acceleration, torque causes angular acceleration. Now, like force, net torque can equal 0, in which case an object isn't angularly accelerating. This is often called statics, a static example of things when objects just aren't accelerating and aren't moving. We kind of looked at that using the example of the teeter-totter last time. But statics is really what any architect spends their entire day doing. They make sure all day, every day, net force equals 0 and net torque equals 0, so that no part of their building is accelerating. Because if a part of their building is accelerating, it's falling, and that's bad. Now, we did teeter-totters, but I also want to show a different example of net torque equals 0 to investigate a few other concepts. With a teeter-totter, you have two different forces pointing in the same direction, but on different sides of a fulcrum. And somehow that still does generate two opposing torques to try to add it to 0. Here, though, we're going to have forces pointing in different directions on the same side of a fulcrum. What I'm picturing here is kind of like an old-timey sign shop. Shop sign. Like you'd see hanging above a door in like a small town downtown sort of thing. And those usually have a physical flagpole that is connected to the building, sometimes by a hinge. The idea being that you could use the hinge to physically lower everything. Say if it's going to be like tornado-y that day, you could lower it to take everything down so that it doesn't risk breaking off and flying away in a storm. So, rather than with the teeter-totter, the fulcrum being in the middle, we're moving the fulcrum to be at the side of this particular piece of metal, and so the pole is going to be bolted to the wall via a hinge. But even when the fulcrum moves, we still want the net torque on this object to be 0. We need the net torque on this object to be 0 so that it isn't accelerating. If this is angularly accelerating, that means it's spinning, and that likely means it's going to spin in this direction and possibly clock someone in the head, which again is bad. So, we need to identify every single torque in this example and make sure they all add up to 0. And in doing so, figure out, the red line here is meant to represent a rope that is physically tied to the flagpole, that being the force that is holding the flagpole up, whereas the weight of this very heavy sign is pulling it down. And so these torques need to cancel out so that the sign stays in place and doesn't start rotating. And we want to figure out how much force is required in that rope so that we can know what type of rope to use. If we pick a rope that's too weak, it's going to snap and then things start spinning, and that is bad. Any questions or issues with the basic setup before we start applying some math? All right. So, flagpole itself is 1 meter long. This is going to be our fulcrum, our pivot point. So we need to figure out what forces are present and how far away from that pivot point they are all going to act. Those forces are all going to generate torques, and they all have to add up to 0. So, first of all, the sign's weight is going to generate torque. The weight of the sign is going to act right here where it's attached, and that is going to be at the very end of the sign, 1 full meter away from where it is bolted to the wall. So, this sign, the torque it generates, torque equals force times radius. The force is going to be the sign's weight, and the radius is going to be the distance between the sign and the fulcrum, which is the full 1 meter length of the pole. That force, if you physically kind of take your hand and act like you were applying a downward force here, and consider what direction that's going to make the whole thing spin, the sign is going to be generating clockwise torque. And to keep it from rotating, we're going to have to introduce some counterclockwise torque to mitigate that, and that's where the rope comes in. Note that an upward pointing force, if applied to this thing, is going to create that needed counterclockwise torque. So if two forces are acting on the same side of the hinge and they point in opposite directions, they generate opposite direction torques. But if it's two forces on different sides of the hinge, like the middle pivot point of a seesaw, the same direction of force can actually generate different direction torques. It's a little, I find it interesting. Here they're opposite direction forces on the same side, so they'll generate opposite direction torques. So the force in this rope is going to be the second force generating torque for us. And where is that force going to be applied to the flagpole?
0.3 meters.
0.3 meters, because the rope is going to physically be tied here, 0.3 meters from the hinge, rather than 1 meter away like the sign's weight is. So, torque rope is going to be added into our total, and that torque is going to be equal to the radius that the rope is tied at from the hinge times whatever force the rope needs to be exerted. And this is ultimately what we're after here. We want to know how much rope tension is required so we don't purchase too weak a rope. So, we got two torques identified here. They have to add up to 0. There is one, and we should know everything we need to at this point to figure out what that needed rope force is. However, there's one catch here that I want to address. If you took this metal bar, attached it to a building via a hinge, and then just left it alone, you don't hang a sign from it and you don't tie the rope, so nothing's tied to it, it's just a metal bar attached to a hinge, what would it naturally do by itself?
Fall down.
It's gonna fall. That means that they're even separated from these torques, there's some other torque here, right? Because otherwise it wouldn't just do this on its own. There's a third torque present. A third torque that is being added into this that also has to add with these to create 0. Can anyone guess what that torque is?
The torque of the pole.
The pole
on the
itself.
hinge.
Yeah, because the force of gravity, like the pole has its own weight. The reason we have to consider that here, where we didn't have to consider that for the seesaw, because technically, if this was a wooden seesaw, like this plank of wood would also have weight, but we didn't think of that last time, right? The reason that we have to consider it here, but not here, has to do with where the fulcrum is. In this example, the fulcrum is directly supporting the object's center of mass. So, new vocab word. Center of mass, alternatively titled center of gravity, I might use these terms interchangeably, can be considered the single spot where the entire mass of the object rests. Technically speaking, if you know where something's center of mass is, you can treat the object as if it was an infinitesimally small point at that spot. And as long as you are acting directly on an object's center of mass, it's as if you are acting directly on the entire object at once. To try to demonstrate this, I have here a 2-meter stick. This one's 2 meters long. And as long as an object is uniform, which is to say made of a single material, there's not like a hole in it or anything like that, or it's not a weird shape, as long as it's made of one solid material, not damaged, and is a standard geometric shape usually, the center of mass is usually going to be dead center of that object, which makes sense, it's its center. So for this meter stick, its center of mass is in its middle at the 1 meter mark. So it's 2 meters long, that's halfway down, 1 meter from either side. That is going to be this stick's center of mass. And as long as I am supporting the center of mass, it's as if I'm supporting the entire object all at once. I've just got one finger on this thing right there at the center of gravity. And if I act on just this one spot, I can move the whole thing. Up, down, and left and right, as long as it doesn't slip. This is what's happening, or what happened, in the teeter-totter. Because as long as this fulcrum is directly under the thing's center, that fulcrum is supporting its center. And the radius between the center, the fulcrum, and the weight of the object is 0. Because if the object's mass is here, this is also the spot where the gravity acts on it. You could consider this entire meter stick to just be a dot right here. As long as I am directly supporting it, it's not going to fall. It's a little wonky, sorry. Same thing here. Fulcrum is under the center of mass, so the object's mass doesn't matter really. The fulcrum is directly countering it, and therefore the weight of the object is not at a radius from the fulcrum. The radius equals 0, so the torque generated by the object's own weight equals 0. However, if the fulcrum is not under the center of mass, so I do this, now that weight is acting at a radius away from the fulcrum, and now it does generate torque, and it starts spinning. So in the case of this signpost, where would this object's center of mass be if it's a solid metal pole, rectangle thing?
5 meters.
5 meters, exactly halfway along its length. Sorry, 0.5 meters, you're right. I didn't say the point for some reason. 0.5 meters, half of 1 meter. Its center of mass should be right there. That is the spot where its weight is going to act. And that force of gravity is now a distance away from the fulcrum. The fulcrum's not directly under it, and that means it's going to make torque. That's why the signpost is going, like, with nothing else attached to it, that's why it spins on its own. So we do have to factor that in here where we didn't in the teeter-totter on Monday. This means there is a third torque and all 3 of them add up to 0. So main things I wanted to look at in this particular case are, 1, torques can all act on the same side of a fulcrum. They can still all multiples add up to 0, even if there's more than 2. And 3, an object, like the rotating object's mass does matter if its center of mass is not being directly supported by the fulcrum. If I ever mention that, say, the flagpole here or the teeter-totter over there is a uniform shape, That's usually your cue that its center of mass is dead center. You should consider if the fulcrum is directly under that or not. I'll try to point out questions where this is or isn't the case. I don't want to make it a trick. I'm just telling you this is a thing that matters in reality. So in this question, we have 3 torques we need to balance, and thankfully we have all the information we need to figure it out. We don't have to go digging for it. But 3 torques to factor in here. First up is the rope. Force rope is what we want to know, but thankfully we know where the rope is tied. We know where the rope is acting, and it's at that 0.3 meters. So R rope is 0.3, F rope is our remaining unknown. The sign, its weight is going to act the full 1 meter away from the hinge, and the force it is exerting is going to be equal to its own weight. So mass of 100 times negative 9.8, force does still point down. That does determine the direction of torque it creates. And lastly, the weight of the flagpole itself. That is acting halfway down its length at its center, so 0.5 meters instead of 1 meter. Its mass is 5 kilograms, and therefore the force it is exerting is its own weight of 5 times negative 9.8. And all 3 of these torques still have to add up to 0. So the weight of the flagpole also makes clockwise torque, like how the weight of the sign does, and now the rope has to work extra hard to keep the whole thing from moving. The flagpole's not going to change it by that much, but again, if they were doing this professionally, you'd need to factor it in to make sure you weren't wrong and the rope doesn't snap. Any questions or issues with our setup so far getting to this point? All right, check the time. F rope is the only unknown, so we are good to solve for it. I'm going to show some of the steps moving forward. Note that both the sign's tension and the pole's torque. The sign's torque and the flagpole's torque are going to end up being negative numbers. This implies the direction that they're trying to make the thing spin in. Because 1 times 100 times negative 9.8 is negative 980. And 0.5 times 5 times negative 9.8 is negative 24.5. Those two both point in a negative direction, which happens to be clockwise here. This means that the rope is going to have to generate counterclockwise torque, and its torque therefore would need to be positive to oppose it. So this torque needs to be positive, and we're likely going to get a positive force from the answer, which makes sense. It's physically pointing up where the others point down. So F rope, bring the negatives over to the other side and divide by 0.3. It's going to be 980 plus 24.5 over 0.3. And I believe that turns out to be, actually I can kind of see what I wrote before I erased it. I'm about to grab my calculator. 3,348.3 newtons. Does anyone's math disagree? Now note, that's a lot of force. That is due, the rather extreme amount of force required here is due to 2 main things. One, that sign is way too big. That's my mass, and you shouldn't be hanging, the weight of an adult human at the end of a 1 meter long flagpole. But for some reason I wrote 100 kilograms in the example and I never changed the image. So, sign is too dang heavy. And secondly, note that the sign radius is about 3 times bigger than the rope supplied radius. And that's why, note again, this thing weighs about 980 newtons. The force is over triple that because the rope is at least 1/2 as far away. Like, the weight of the sign is 3 times further away, so you need to exert 3 times at least the force to hold it up. So if you're ever using a tool that involves torque, always try to hold it by the very end of its handle to generate as much torque as possible. Never hold a hammer directly under the head, then you're just punching something with the metal side. Same true with crowbars. And I guess swords, if any of you ever find yourself using a sword. Axes are more commonly used these days. Any questions on this one for right now? All right. I also wanted to use this one to bring up the notion of center of mass. Again, just to reiterate, an object's center of mass is considered the one spot where all of its mass lives. Usually it's in the object's center, again, as long as it is a uniform geometric shape and made mostly out of a single material. And I'll bring up the sorts of cases where center of mass matters. I just want to give a few examples. One, center of mass is why, when we were talking about gravity last week, all of our answers were in terms of the distance between core to core, rather than surface of Earth to surface of Moon, because the center of mass is, it's where all the mass is, therefore it's the center of the gravitational effect. Earth's gravity is concentrated in its core at its center of mass, because the mass is what creates the gravity, and that's the one spot where functionally all of its mass lives. Technically, if the Earth was, the size of a dime, but it had the same mass and that dime was still right here, it would have the same effect on the moon. As long as its mass total is the same, and as long as it's in the same spot. Doesn't matter what the Earth's size is, just its mass. It also means if you ever need to move an object around, it is easiest if you apply the force directly to its center of mass. Because if you push on something's center of mass, you are effectively pushing on the entire object at once. If you ever need to kick a door open, aim center of the door, because you want to accelerate the door's entire mass. Well,
unless you kick at its.
Actually, yeah, door's a weird example because there's torque involved. So,
Opposite side of the hinges.
yeah, you'd want to kick in the center axis, but you'd put your foot over here to generate as much torque as possible. So door's kind of weird. Better example. If you ever needed to, heaven forbid, kick a person away from yourself, you want to kick center mass. Humans are weird shapes, but it's usually somewhere in their torso. And if you kick their center of mass, you kick the entire person at once. Again, I did Taekwondo, so a weird amount of my examples involve kicking things. So if you act on center of mass, you act on the whole object at once. That's why the seat belt goes on this part of you. As long as your torso moves with the car seat, the rest of you will too. Parachutes too. It's also why it's really bad if you have to hang from your arms on something. That's not your center of mass. If you get yanked around by your arm, it's going to be a bad time. Now, this is to kind of segue from this point onto the next thing we need to talk about. Center of mass is important to rotation. An object's mass does affect how it wants to rotate. But usually things want to spin about their center of mass. All the examples we've done with torque up till now have all been absent of spinning. Like, I erased the teeter-totter. The teeter-totter and this signpost thing we just did, the torque's equal 0 when things weren't spinning. However, things can spin. If you imbalance the torques, you will cause angular acceleration and things will start spinning. For example, the reason there's an airplane pictured right now is if you are piloting the plane and you want to roll, I think this is an aileron roll, I keep wanting to say barrel roll, but there's memes about that. For this plane to spin, the flaps on either wing need to be angled such that there's a force pointing this way on one wing and the opposite way on the other wing. And those will both generate torque pointing in the same direction to cause the plane to start spinning around its center of mass. Interestingly though, its linear speed might not change when it does this. If it's flying in a straight line, it might still be moving at 30 miles per hour. It's just spinning while it does that. So net torque and net force can exist separately from one another. Like the net force on the plane could be 0 and it could stay at the same linear speed even if it is angularly accelerating. But the main thing I want to focus on here is when torques are imbalanced, that does cause angular acceleration. Like again, how imbalanced linear force causes linear acceleration. And how much an object accelerates depends on the magnitude of the net force or torque, but also on its mass. And I've kind of hand-waved at this formula a few times now. I've tried to compare, torque to force and acceleration to angular acceleration. You noticed what part of the formula I haven't mentioned yet? It's that letter I in the middle. This sits where mass is supposed to sit. These formulas are counterparts to each other. Torque and force are counterparts. Acceleration and angular acceleration are counterparts. Therefore, mass and this new thing are counterparts to one another. I haven't mentioned it yet because I kind of hate that mass has an angular counterpart. I don't think it should have one, but it does. Mass isn't a vector, so it's kind of weird that we need to convert it into some sort of angular form. But the problem is that two objects with the same mass might have different tendencies of rotation depending on their shape and how you make them spin. For an example, I'm going to make this thing spin. This is just a notebook. Pretty sure it was a prize I got somewhere, so it's Presbyterian College branded. And this object, I'm just going to say we can treat it as a general boxy shape. It's a big old rectangle sort of thing. Uniform geometric shape, made out of a uniform enough material. It's all mostly carbon in here. So uniform object, and I'm going to try to make this spin 3 different ways. Because it has at least, it's a 3D shape, it has at least 3 different axes. I'm going to spin it 3 different ways, and I want you to notice how it spins through all of them. First way I'm going to spin it is like this. I'm going to spin it through the center of its flattest side, its biggest side. So I'm going to throw it into the air like this, and I want you to note how fast it goes when I do that. Alright, that's our baseline speed. Now I'm going to switch axes. I'm going to go from this to this. So I'm just going to tilt it slightly, tilt it 90 degrees, and throw it through this axis instead. So note again the speed. Now on average, how did that compare to this? Just in terms of angular speed.
Fewer rotations.
Fewer rotations, and this way creates chaos, first of all. Doing it this way creates a slightly faster angular speed. Does that seem accurate? I know it's a little hard to tell. But I'm trying to apply the same force each time. It does generally spin slower this way. You guys think you're seeing that? Okay. Now it's the same object, same mass, but changing the axis that it's spinning through affected how much the torque affects it. But this thing has a third axis, so instead of this or this, I can also do it like this. And I want you to really watch this one. This is where it gets weird. Did you see it? You might have noticed this if you've ever tossed a book or your cell phone idly into the air, because it's the same basic shape. What does this thing do when I use this axis?
It rotates upon two different axes as well.
Yeah. Colloquially, I just kind of call it like a backflip. Like more than it's already backflipping. This thing, shapes like this, hate spinning that way. They don't want to do it. And they literally stop partway through and swap sides just to avoid it. Like, again, I'll do it as slowly as I can. It hated it so bad that it destabilized and spun about a different axis for a second. And so it landed oriented differently. Again, any similar object like this will do that if you throw it through that particular side. Same object, same linear mass, but that mass reacted differently depending on how it was spinning. This means that we can't just plug m into the formula anymore. I wish badly that I could just write m here. I really do. But that, just now, I'm meaning to serve as proof that the same m still reacts differently in all three scenarios, so we can't just use m. Instead, we have its counterpart, I, and I stands for moment of inertia, written here. I equals moment of inertia, and it serves as the angular counterpart to mass. Displacement has angular displacement, velocity has angular velocity, acceleration has angular acceleration, force has torque, mass has moment of inertia. They're all counterparts to one another. And it's why on your formula sheet, if you look at these linear formulas here, set against their angular counterparts, wherever you see an m in the linear ones, you've got an I in the angular ones. So mass m, its counterpart in the angular world is moment of inertia I. And moment of inertia is a measurement of how easily it is to make something spin through a specific axis based on axis of choice and also its shape. Because it's not only which axis you choose to spin something through, different shapes have different tendencies to rotate to different degrees. Off the top of your head, what do you think is the easiest shape to make spin? Circles. And that's why, that's one reason why, bike tires, all tires, are shaped the way that they are. Wheels spin easiest, and I can actually prove that looking at this formula here, because this chart right here, these are all different moment of inertia formulas for different shapes and spinning through different axes. And out of all these formulas, just looking at the round objects that would roll, the one that is lowest is a sphere, which is basically just a wheel that's slightly thinner. So wheels roll easier than other shapes. As long as it's the same mass and the same radius, a wheel will have the smallest moment of inertia, therefore it has the easiest time rolling. And that's why doing this is very straightforward. Doesn't take a whole lot of force. But different shapes have different tendencies to rotate, and that's why some shapes are easier to roll than others. And even the same shape wants to spin differently through different axes. Because if I wanted to, I could try to spin this thing like a top. And this is harder. This is required. Sorry. Please don't break. Cool. This requires more force, like my hand is exerting more effort right now, and it's also not even spinning as fast. This is just harder because the wheel doesn't want to spin this way. It has an easier time spinning this way because the formula for this has a smaller moment of inertia than the formula for this. And if I encourage you to actually come try this yourself just to feel the difference. I'm just going to leave the wheel over here. Give it a shot. And I give you a few more things you can do with this wheel on Friday, just to demonstrate this stuff. But what this chart means is every single one of these different shapes and different ways of spinning something has a slightly different moment of inertia formula. Because some ways to spin things are just easier than others. Now, you don't have to memorize any of these, because there's too dang many of them. For that reason, a better version of this chart is actually on the back page of your formula sheet. You have all these information already back here. And all these formulas are very similar if you take a look at that. I know the board might be a little blurry right now. If you look at the formula sheet itself, just to see them more clearly, you'll note the formulas are all basically the same. Excuse me. They all involve mass times radius squared or length squared. The only real difference is the fraction out front of them. And the fraction is just meant to tell you which shape is easiest to spin. Again, out of the normal rolling shapes, the solid sphere is lowest, although the lowest fraction here is the 1/12 on the rod or plate rotating through their centers. And in any question where this sort of thing matters, I will always tell you what shape something is and how it is rotating through. So that means that if a question mentions, for example, that you are about to spin the wheel of fortune and that you may consider the wheel to be a uniform cylinder rotating through its center, that means you can check that table and note uniform cylinders. Their moment of inertia is equal to 1/2 times their mass times their radius squared. I would make sure you'd have mass and radius squared and that you know what shape something is so that you can use this chart to figure that out. I kind of hate moment of inertia, if I'm being honest. I hate that I can't just put mass in the formula and make it work. I hate having to take this step. This is tied for my least favorite part of what I do, if I'm being honest. My real least favorite part is too much algebra all at once. Even I get sick of it, if I'm being honest. But this is my second least favorite thing. But I will make sure that in any case where you would need it, you would know what shape you're dealing with and that it would be one on this chart that you can confer with. If you ever have to use moment of inertia, like say in the torque formula, you'll have everything you need to figure it out. I'll tell you the shape, you know mass and radius so that you can find what you need to plug in. All you need to know about it is different shapes just want to spin to different degrees. And you'll always know what shape you can consider something. I will make sure that the question tells you. Sound fair? I hope. All right. Well, let's do a little bit of practice. Let's actually spin the wheel. Wheel of fortune. We're going to consider it to be a uniform cylinder, because that's technically what a disc is. It's just a really thin cylinder. The wheel has a radius of 1.5 meters, a mass of, 45 kilograms, and you, standing at the edge of the wheel, are going to grab it and exert a force of 23 newtons tangent to its edge, which means perpendicularly to its radius.
Are we using the 2 meters or the 1.5 meters radius?
Whoops. I guess it's 2 meters, and I misremembered my own example. Thank you for pointing that out. Sorry. The wheel's radius is 2 meters. It's a big old thing. Gotta make sure you can see it on camera. So, we are going to spin this wheel, and we want to know what its angular acceleration is going to be when you apply that force. So, when you exert that force on that wheel, what you're actually generating is torque, since that force is a distance away from the central axis it's going to spin around. So you're going to generate torque, and that's going to cause it to spin based on its moment of inertia. So if our goal is to find alpha, we first need to figure out how much torque we're creating and also find the moment of inertia of this disc. Now, we've only talked about 2 formulas that have torque in them, and This is one of them. So what formula should be used to determine the amount of torque we create on this thing? You know, we know the force we're exerting, and we know the radius of the wheel, so we can figure out how much torque we're generating.
Torque equals I, moment of inertia times angular speed. Or
Angular acceleration,
Angular
and that's this
acceleration.
formula. Basically, we're going to combine the two torque formulas to figure out alpha. My alpha was kind of weird, actually. So for torque, we're going to use radius times force. So again, just kind of combining the two formulas together. Radius times force equals moment of inertia times alpha. But we also need to figure out the moment of inertia of this very flat cylinder. So, again, it says here, always make sure you know what shape something is. Uniform cylinder, so it's not hollow, it's just going to spin throughout its own middle axis. So that means that you can check the chart, solid cylinder or disc, I is 1/2 mass times radius squared. And again, they're all mass times radius or length squared. It's just a matter of what fraction you need to hunt down. So instead of I, 1/2 mr squared times our unknown alpha. Thankfully, we do know all of these things except alpha, so with these substitutions made, we are good to go. Disc's radius is 2, applied force is 23 newtons, 1/2, mass of, mass of 45 kilograms, radius of 2 squared, and alpha is our remaining unknown. After all that, please let me know if your math disagrees. Alpha should come out to be about 0.51 repeating radians per second squared. So if you grab the wheel and you are physically acting on it for a full second, it should speed up from 0 to 0.51 rad per second. And the longer you're acting on it, the faster it would go from there. But that is the rate at which it would speed up. Yes?
Is it bad to assume, like, we had the force pointing down, since you're, like, spinning the wheel down instead of up?
Oh. That wouldn't end up mattering here more, really.
Would it just change the sign of the alpha?
Potentially, yes. Like, if we were comparing the effect that would have, one of these forces would be negative, therefore one of the alphas would be negative.
Okay.
Which just means, yeah, it would spin in the opposite direction.
You wouldn't have counted it wrong if we, like, had the initial 23 newtons pointing down?
No.
Okay.
Odds are I would ask for the magnitude of the acceleration, since, like, the larger context of this particular question doesn't really care about it necessarily. If there was a question that involved multiple forces in different directions interacting, then one of them would have to end up being negative, and you'd have to consider that. It didn't end up mattering here. It's good to consider, but there's just the one force, the one direction of motion, so you can just decide if it's positive or negative or not, and then the answer is just correct as long as it's the same direction as you picked. Does that answer the question?
Mm-hmm.
Okay. How you guys feeling? All right. And I'll say it again, moment of inertia is one of my least favorite parts of this job. So if it feels weird, it feels weird to me, and I do this for a living, so that's valid on your part. Friday, we are going to practice it a little bit more, try to make sure it makes sense. Namely by looking at the last couple angular counterparts we have on our agenda, namely how moment of inertia factors into angular momentum and angular kinetic energy. And that'll be how we close out chapter 8. So, any last minute thoughts before we break? All right, I'm gonna do you guys need anything, and have a great day.
When's our test again?
The week of November 13th through 17th, you will take it during lab time on one of those days.
13th or 17th, all right.
Yes, and that is, hold on. I'm a visual person, I need to look at a calendar or it's not real.
Elise, how many have you collected?
It's a 19.
I'm at 16. I'm about to go collect.
Of course, the nuclear project is.
Yeah, that is technically in 2 or less weeks, depending on what day you take it.
Gotcha.
But, like this week, we're gonna finish rotation. Next week, we're gonna spend like half of the week on chapter 9, which should leave us Friday the 10th, and also the week of the test to review.
Yeah.
Like after Friday, I'm only teaching you a couple tiny more things. Like there's only a few more things. I got a week more of learning before the test.
All right.
Yeah, half my stuff isn't even dried out. Like I collected.
And then it's Thanksgiving break. That's nice,
I had
right?
to collect a new goldenrod because I didn't realize that mine didn't have roots.
Were the goldenrods the yellow flowers from Lake Raven?